What's the most powerful thing in the universe? Is it the crushing pull of a black hole, the blinding flash of a gamma-ray burst, or something even stranger? In this journey, we'll uncover the hidden forces that shape reality itself, follow the trail through the most extreme events in the cosmos, and explore what might truly deserve to be called the most powerful. By the end, you'll see the universe in a way you never have before. Before we begin, share your guess in the comments. What do you think is the most powerful thing in existence? And if you love exploring big cosmic questions, make sure to like, subscribe, and hit the bell so you don't miss what's coming next. Look around you. Everything you see, everything you touch, everything you are is made of tiny, invisible pieces. These pieces are the building blocks of reality, connecting you to the farthest reaches of the cosmos in ways you might never have imagined. From the smallest atom to the largest galaxy, everything is woven together by a set of fundamental forces. These forces are the silent architects of the universe, shaping the structure of matter and the dance of celestial bodies across the vastness of space. And these pieces are held together, or pushed apart, by forces we can barely imagine. Without them, the universe would be a chaotic sea of particles, never forming stars, planets, or life itself. But what if I told you that the most powerful thing in the entire universe isn't a giant explosion, or a crushing black hole, or even the incredible energy of the Big Bang itself? The answer is more subtle, more profound, and more essential to the very existence of everything. Understanding these forces isn't just a scientific pursuit, it's a journey to comprehend our place in the cosmos. By exploring the nature of power on the grandest scales, we unlock secrets about the origins of matter, the fate of stars, and the very fabric of reality itself. What if the true power lies in something far more fundamental, something that shapes reality from the smallest atom to the largest galaxy? The quest to find the most powerful thing in the universe is a quest to understand the rules that govern everything. Join us as we embark on a cosmic journey to uncover the ultimate question: what's the most powerful thing in the universe? The answer may change the way you see everything. To truly grasp the power that shapes our universe, we must first unravel the secrets of the fundamental forces. Picture the universe as a vast, intricate machine. Every star, planet, and atom is a moving part, and these forces are the gears and levers that keep everything in motion. They are the invisible threads weaving the fabric of reality. For centuries, philosophers and scientists have wondered, what holds everything together? From the apple that inspired Newton to the orbits of distant planets, these questions led to some of the greatest discoveries in science. The answer lies in four fundamental forces, each with its own unique role. These forces govern everything, from the tiniest particles in an atom to the largest clusters of galaxies. They are the strong nuclear force, the weak nuclear force, the electromagnetic force, and gravity. Let's explore each one and see how they shape the cosmos. First, the strong nuclear force. Imagine it as the universe's ultimate superglue. It binds protons and neutrons together in the heart of every atom, overcoming the powerful repulsion between positively charged protons. Without it, atoms would simply fly apart. The strong force is the mightiest of all, but it only works at incredibly tiny distances, about 100,000th the width of a human hair. If you try to pull two protons apart, its strength drops off almost instantly. It's like a super strong magnet that only works when the magnets are nearly touching. This force was discovered in the 20th century as scientists probed the mysteries of atomic nuclei. It's about 100 times stronger than the electromagnetic force, but only within the nucleus. Without it, there would be no atoms, no chemistry, and no life. Next, the electromagnetic force. This is the force you encounter every day. It's responsible for electricity, magnetism, and light. It's what makes magnets stick to your fridge, powers your phone, and even allows you to see. The electromagnetic force acts between charged particles. Opposites attract, likes repel. It has an infinite range, stretching across the universe, but its effects can cancel out when positive and negative charges balance each other. This force is behind all chemical reactions, binding atoms into molecules. It's the reason you feel solid ground, the force behind your brain's electrical signals, and the spark in every lightning bolt. Discovered in the 19th century, it revolutionized technology and our understanding of nature. Now, the weak nuclear force. It's less famous but absolutely vital. The weak force is responsible for radioactive decay, transforming one type of particle into another. It's the engine behind the sun's energy, allowing hydrogen to fuse into helium and release light and heat. The weak force operates at even shorter ranges than the strong force, but its effects are everywhere, from the warmth of the sun to the radioactive elements deep inside the Earth. It was first identified in studies of beta decay, a process that helps power nuclear reactors and medical imaging. Without the weak force, the sun would not shine, and life as we know it would not exist. It also plays a key role in the creation of elements inside stars, fueling the cosmic alchemy that builds the universe. Finally, gravity. It's the most familiar force, yet also the most mysterious. Gravity is what keeps your feet on the ground, the moon in orbit, and galaxies bound together. But compared to the other forces, it's astonishingly weak. What gravity lacks in strength, it makes up for in reach. It acts between anything with mass or energy, and its effects add up over vast distances. That's why gravity dominates the grandest scales, shaping stars, galaxies, and the entire cosmic web. Gravity was the first force to be described mathematically, thanks to Newton and later Einstein, whose theory of general relativity revealed that gravity is the warping of space and time itself. It's the sculptor of the cosmos, shaping its architecture over billions of years. So which is the most powerful? The strong force is mighty but short-ranged. The electromagnetic force is versatile and infinite, but often cancels itself out. The weak force is essential for transformation and energy, but subtle. Gravity, though weak, rules the largest scales, binding the universe together. Each force has its own domain of immense power, and together their interplay creates the dynamic, complex universe we inhabit. The next time you look at the night sky, remember, it's these four forces, working in harmony, that make everything possible. If the fundamental forces are the architects, then black holes are some of the universe's most extreme and powerful creations. They are cosmic devourers, regions of space-time where gravity is so incredibly strong that nothing, not even light, can escape. But what exactly are black holes, and why do they fascinate scientists and the public alike? The idea of a black hole was first proposed in the 18th century, but it wasn't until Einstein's theory of general relativity that the concept truly took shape. For decades, black holes were thought to be purely theoretical, but mounting evidence has shown they are not only real but common throughout the universe. The concept of a black hole might sound like something out of science fiction, but they are very real and play a crucial role in the evolution of galaxies. In fact, astronomers have now observed the effects of black holes on their surroundings, confirming their existence beyond doubt. So, how do black holes form? The most common way is from the death of a massive star. When a star much larger than our Sun runs out of its nuclear fuel, it can no longer support itself against its own immense gravity. The core collapses inward with incredible speed and force, leading to a spectacular explosion called a supernova. How do these incredible objects form? The most common way is from the death of a massive star. When a star much larger than our Sun runs out of its nuclear fuel, it can no longer support itself against its own immense gravity. The core collapses inward with incredible speed and force, leading to a spectacular explosion called a supernova. But not all black holes are born from dying stars. Some may have formed in the earliest moments after the Big Bang. These are called primordial black holes, and they could be as small as an atom or as massive as a mountain. While still hypothetical, their existence could help explain some of the universe's greatest mysteries, such as the nature of dark matter. What's left behind is an incredibly dense remnant. If this remnant is massive enough, its gravity becomes so intense that it collapses further, crushing itself down to an infinitely small point called a singularity. This is the heart of a black hole. There are three main types of black holes: stellar mass, intermediate mass, and supermassive. Stellar mass black holes are formed from collapsing stars, while intermediate mass black holes are thought to form from the merging of smaller black holes. Supermassive black holes, found at the centers of galaxies, can be millions or even billions of times the mass of our Sun. There are different types of black holes: stellar mass black holes, which are typically a few to a few dozen times the mass of our Sun, and supermassive black holes, which can be millions or even billions of times the mass of our Sun, residing at the centers of most large galaxies, including our own Milky Way. Intermediate mass black holes are the missing link, and astronomers are still searching for definitive evidence of their existence. Recent discoveries of unusually massive black holes in star clusters may finally be revealing these elusive objects. The most defining feature of a black hole is its event horizon. Imagine it as a one-way door. Once anything crosses this boundary, whether it's light, matter, or even information, it can never escape the black hole's gravitational pull. It's not a physical surface, but rather a point of no return. Contrary to popular belief, black holes do not suck everything in like a cosmic vacuum cleaner. If our Sun were replaced by a black hole of the same mass, Earth would continue orbiting as usual, just in darkness. It's only when you get very close to the event horizon that the effects become truly extreme. The gravity near a black hole is so extreme that it warps and distorts the very fabric of space-time around it. Think of space-time as a stretched rubber sheet. A heavy ball placed on it would create a dip. A black hole, with its immense mass concentrated in a tiny area, creates an incredibly deep, inescapable well in this sheet. This extreme warping is what gives black holes their immense power to pull everything towards them. This warping of space-time can be so intense that it creates phenomena like gravitational lensing, where light from distant stars is bent around the black hole, producing stunning visual effects and even multiple images of the same object. While nothing can escape a black hole once it crosses the event horizon, black holes are far from inert. They are often surrounded by swirling disks of gas and dust called accretion disks. As matter falls towards the black hole, it doesn't just plunge straight in. Instead, it forms a disk, spiraling inward like water going down a drain. These accretion disks can reach temperatures of millions of degrees, emitting X-rays and gamma rays detectable across the universe. The intense friction and magnetic fields within the disk can also launch powerful jets of particles at nearly the speed of light, shooting out from the black hole's poles. This matter gets incredibly hot due to friction and gravitational forces, emitting vast amounts of X-rays and other forms of radiation. This process of accretion is one of the most efficient ways in the universe to convert mass into energy, far more efficient than nuclear fusion in stars. The energy released from these accretion disks can be truly staggering, making black holes some of the brightest objects in the universe, even though the black hole itself is invisible. In 2019, astronomers captured the first ever image of a black hole's shadow using the Event Horizon Telescope. This historic achievement provided direct visual evidence of a black hole and confirmed predictions made by Einstein's theory a century earlier. Supermassive black holes, found at the centers of galaxies, have an even more profound influence. They are not just passive cosmic vacuum cleaners. They actively shape the evolution of their host galaxies. The energy released from their accretion disks and powerful jets can heat and push away gas, influencing how many new stars can form in the galaxy. This connection, known as black hole feedback, is a critical piece of the puzzle in understanding how galaxies grow and change over cosmic time. The power of a black hole isn't just in its ability to consume, it's also in its ability to influence and sculpt the universe around it on the grandest scales. In fact, the mass of a galaxy's central black hole is closely linked to the size and properties of the galaxy itself, a relationship known as the M-sigma relation. This suggests that galaxies and their black holes grow and evolve together, each influencing the other's fate. Black holes can also merge with one another, creating even larger black holes and sending ripples through space-time known as gravitational waves. These waves were first detected in 2015, opening a new window into the study of the universe and confirming yet another of Einstein's predictions. Despite their fearsome reputation, black holes are essential to the cosmic story. They recycle matter and energy, drive galaxy formation, and help us probe the most extreme laws of physics. In many ways, black holes are not just destroyers but creators, shaping the universe in ways we are only beginning to understand. If black holes are cosmic devourers, then quasars are their most spectacular and luminous manifestations. Imagine a lighthouse so incredibly bright that it outshines an entire city, or even an entire country. Now imagine a cosmic lighthouse that outshines billions of stars in its own galaxy, and sometimes even the entire galaxy itself. That's a quasar. The story of quasars began in the late 1950s and early 1960s, when astronomers using radio telescopes detected mysterious, extremely bright sources of radio waves in the sky. These objects, dubbed quasi-stellar radio sources, or quasars, appeared star-like through optical telescopes, yet their light was unlike anything seen before. It wasn't until astronomer Martin Schmidt analyzed the spectrum of one such object in 1963 that the true nature of quasars was revealed. The light from these objects was redshifted far beyond any known star, indicating they were not only incredibly bright, but also unimaginably distant, billions of light-years away. These are not just ordinary galaxies. They are active galactic nuclei, powered by supermassive black holes that are furiously feeding at an astonishing rate. Quasars are among the most distant objects we can observe, acting as cosmic beacons that illuminate the far reaches of the universe. Their light has traveled for billions of years, giving us a glimpse into the universe's ancient past. Quasars are essentially supermassive black holes that are actively gobbling up vast amounts of gas and dust from their surroundings. As this matter spirals into the black hole, it forms an incredibly hot and dense accretion disk, just like we discussed. But in quasars, this process is happening on an extreme scale. The friction and gravitational energy released are so immense that the disk glows with an intensity that can be thousands of times brighter than the entire Milky Way galaxy. This isn't just light, it's energy across the entire electromagnetic spectrum, from radio waves to X-rays and gamma rays. The mechanism of energy release in quasars is truly mind-boggling. As matter falls into the black hole, a significant fraction of its mass is converted directly into energy, following Einstein's famous equation E equals mc squared. This process is far more efficient than nuclear fusion in stars. In addition to the glowing accretion disk, many quasars also launch powerful jets of superheated plasma, traveling at nearly the speed of light, extending hundreds of thousands of light-years into space. These jets are thought to be powered by the spinning black hole and the magnetic fields within the accretion disk, acting like cosmic particle accelerators. The sheer amount of energy contained within these jets is immense, capable of influencing the intergalactic medium and even the formation of other galaxies. Observing quasars requires powerful telescopes, both on the ground and in space. Astronomers use a variety of instruments to study their light across the electromagnetic spectrum, from radio waves to visible light and X-rays. Each wavelength reveals different secrets about the quasar's structure and the environment around it. Because quasars are so bright and distant, they serve as cosmic backlights, allowing scientists to probe the material that lies between us and them. By analyzing how the quasar's light is absorbed by intergalactic gas, astronomers can map the large-scale structure of the universe and study the evolution of galaxies over billions of years. Quasars are not just powerful, they are also incredibly important cosmic signposts. Because they are so bright, we can observe them from incredibly vast distances, meaning we are seeing them as they were billions of years ago, when the universe was much younger. This makes them invaluable probes of the early universe. By studying quasars, astronomers can learn about the conditions of the early cosmos, how galaxies formed and evolved, and even the distribution of matter in the universe when it was just a fraction of its current age. They are like cosmic time capsules, sending us messages from the dawn of time, revealing the universe's most energetic and dynamic period. Their existence tells us that the early universe was a place of incredible activity and immense power, shaping the cosmic landscape we see today. In fact, some of the most distant quasars we observe formed less than 1 billion years after the Big Bang, providing crucial clues about the formation of the first galaxies and the growth of supermassive black holes in the early universe. The power of quasars reminds us that the universe is a place of constant change and extreme phenomena. From the fundamental forces that bind atoms to the gravitational might of black holes and the radiant fury of quasars, we are only just beginning to grasp the true scale of cosmic power. But there's more to explore, even more powerful events and mysterious forces that shape our reality. Stay with us as we continue our quest to find the most powerful thing in the universe. From the steady glow of stars, we now turn to their dramatic and explosive finales, supernovae and hypernovae. These aren't just pretty fireworks in the night sky. They are some of the most energetic events in the universe, capable of outshining entire galaxies for a brief period. But to truly understand these cosmic cataclysms, we must first explore the life cycle of stars themselves. Stars are born in vast clouds of gas and dust called nebulae. Over millions of years, gravity pulls this material together, forming dense clumps that heat up and ignite nuclear fusion. This marks the birth of a new star, a process that has been happening for billions of years across the cosmos. Once formed, a star spends most of its life fusing hydrogen into helium in its core, shining steadily for millions to billions of years. The mass of a star determines its fate. Smaller stars, like our Sun, live long, stable lives, while massive stars burn brighter and faster, setting the stage for spectacular endings. As a massive star exhausts its hydrogen, it begins fusing heavier elements, helium into carbon, carbon into oxygen, and so on, creating layered shells like an onion. This process continues until iron forms in the core. At this point, fusion can no longer produce energy, and the delicate balance between gravity and pressure collapses. They are the cosmic furnaces where the elements essential for life are forged and then scattered across the cosmos. The star's core collapses in a fraction of a second, triggering a titanic explosion, a supernova. The outer layers are blasted into space, while the core may become a neutron star, or, if massive enough, a black hole. This is one of the most violent events in the universe. A supernova is essentially the spectacular death of a massive star. Imagine a star like our Sun, but many, many times bigger, at least 8 times more massive. Throughout its life, such a star generates energy by fusing lighter elements into heavier ones in its core, like hydrogen into helium, then helium into carbon, and so on, all the way up to iron. The first recorded supernova visible to the naked eye was observed by Chinese astronomers in 185 AD. Centuries later, in 1604, Johannes Kepler documented a brilliant supernova in our own galaxy, forever changing our understanding of the heavens. This fusion process creates an outward pressure that balances the inward pull of gravity. But iron is different. When a star tries to fuse iron, it actually consumes energy instead of releasing it. The collapse and explosion of a supernova can briefly outshine an entire galaxy. For a few weeks, a single dying star can radiate as much energy as billions of suns. So once the core becomes mostly iron, the star runs out of fuel. The outward pressure vanishes and gravity wins. The core collapses in a fraction of a second, reaching incredible densities and temperatures. This sudden collapse then rebounds, sending a shockwave outward that blasts the star's outer layers into space at tremendous speeds. There are several types of supernovae. Type 2 supernovae result from the core collapse of a single massive star, while Type 1a supernovae occur in binary systems, when a white dwarf accumulates too much mass from its companion and ignites in a runaway fusion reaction. There are different types of supernovae, but the most common ones we talk about are Type 2 and Type 1a. Type 2 supernovae are the core collapse events we just described, resulting from the death of a single massive star. They leave behind either a neutron star or, if the original star was massive enough, a black hole. Type 1a supernovae have played a crucial role in modern astronomy. Because they all explode with nearly the same intrinsic brightness, they serve as standard candles, allowing astronomers to measure vast cosmic distances and even discover the accelerating expansion of the universe. Type 1a supernovae, on the other hand, are a bit different. They occur in binary star systems where a white dwarf star, the remnant of a less massive star like our Sun will become, siphons matter from a companion star. As the white dwarf gains mass, it eventually reaches a critical limit, triggering a runaway nuclear fusion reaction that completely obliterates the star. Both types are incredibly powerful, but Type 1a supernovae are particularly important because they all explode with roughly the same intrinsic brightness, making them excellent standard candles for measuring cosmic distances and the expansion of the universe. The energy released in a supernova explosion is almost beyond comprehension. In just a few weeks, a single supernova can radiate as much energy as our Sun will produce over its entire 10 billion-year lifetime. Most of this energy is not visible light, but a torrent of neutrinos, tiny, nearly massless particles that stream out from the collapsing core. In fact, about 99% of a supernova's energy is carried away by neutrinos, a discovery confirmed by detectors on Earth during supernova 1987A. Most of this energy, surprisingly, is not in the form of light, but in a flood of tiny, elusive particles called neutrinos. These neutrinos carry away about 99% of the explosion's energy, leaving behind a brilliant, albeit temporary, cosmic beacon. This immense energy is what drives the expansion of the stellar material, creating the beautiful and intricate supernova remnants we observe. These remnants, like the famous Crab Nebula, are cosmic laboratories. They enrich the interstellar medium with heavy elements, providing the raw materials for new stars, planets, and even life itself. But supernovae are more than just spectacular explosions. They are the universe's alchemists. Stars, during their lives, can only fuse elements up to iron, elements heavier than iron, like gold, silver, uranium, and even the calcium in your bones and the iron in your blood, are primarily forged in the extreme conditions of a supernova explosion. The intense heat and pressure during a supernova allow for rapid neutron capture, a process known as the R process. This is how the universe creates its heaviest elements, which are then scattered across space to become part of new worlds. The intense temperatures and pressures, combined with the flood of neutrons, allow for rapid nuclear reactions that create these heavier elements. When the star explodes, these newly forged elements are scattered across the galaxy, enriching the interstellar gas and dust. This enriched material then becomes the building blocks for new generations of stars, planets, and ultimately life. Without supernovae, the universe would be a much simpler, less interesting place, devoid of the complex chemistry necessary for our existence. In recent decades, astronomers have used powerful telescopes and computer simulations to witness supernova in distant galaxies and model their intricate physics. These discoveries have deepened our understanding of how stars live, die, and transform the universe. And then there are hypernovae, the even more extreme cousins of supernovae. These are truly colossal explosions, even more powerful than typical supernovae, and they are thought to be the origin of the most energetic phenomena in the universe: long gamma-ray bursts. Hypernovae occur when the most massive, rapidly spinning stars collapse. Instead of a spherical blast, they unleash powerful jets of matter and energy from their poles, producing the brightest explosions ever observed. A hypernova occurs when an extremely massive, rapidly rotating star collapses. Instead of a relatively spherical explosion, the collapse in a hypernova is thought to produce powerful, collimated jets of matter and energy that blast out from the star's poles. These jets are what generate the gamma-ray burst. The connection between hypernova and long gamma-ray bursts was confirmed in 1998, when astronomers observed a gamma-ray burst coinciding with a supernova in a distant galaxy. This discovery revealed the true power of these cosmic explosions. The link between hypernova and long gamma-ray bursts is one of the most exciting discoveries in modern astrophysics. It tells us that these two seemingly different phenomena are intimately connected, both representing the cataclysmic death of the most massive stars. The energy released in a hypernova is truly staggering, far exceeding that of a regular supernova. It's a testament to the universe's capacity for both creation and destruction, where the most violent events also sow the seeds for future complexity. These stellar explosions are not just powerful, they are fundamental to the cosmic cycle of matter and energy, constantly reshaping the universe and providing the raw materials for everything we see and are. In the grand tapestry of cosmic evolution, supernovae and hypernovae are both destroyers and creators. They end the lives of stars, but in doing so, they seed the universe with the elements and energy needed for new stars, planets, and life to emerge. Without these explosive events, the universe would be a far less dynamic and wondrous place. From the explosive death of stars, we now turn our attention to the most powerful and mysterious explosions in the universe. Gamma-ray bursts, or GRBs. These cosmic flashes are so intense, so brief, and so distant that for decades, they puzzled astronomers and challenged our understanding of the universe. Imagine a flash of light so incredibly bright that, for a few fleeting seconds, it outshines every single star in the entire observable universe combined. That's the kind of power we're talking about with a GRB, an event so energetic that it can release in seconds what our sun will emit over its entire lifetime. But what exactly are gamma rays? Gamma rays are the most energetic form of light in the electromagnetic spectrum, far more powerful than X-rays or visible light. GRBs are short-lived bursts of these high-energy photons, lasting from a few milliseconds to several minutes, and they are among the most luminous events ever observed. The story of their discovery begins in the late 1960s, at the height of the Cold War. Satellites launched to detect secret nuclear tests unexpectedly picked up mysterious flashes of gamma rays coming from deep space, not from Earth. This accidental discovery opened a new window into the cosmos and sparked decades of scientific intrigue. For years, the origin of these bursts remained one of the biggest mysteries in astrophysics. Were they coming from our own galaxy or from far, far away? It wasn't until the 1990s, with the launch of more advanced satellites like NASA's Compton Gamma Ray Observatory and BeppoSAX, that astronomers could pinpoint their locations and confirm that GRBs originate from distant galaxies billions of light-years away. Today, we know that there are two main types of GRBs, classified by their duration and origin: long GRBs, which last more than 2 seconds, and short GRBs, which last less than 2 seconds. Each type tells a different story about the violent processes shaping our universe. Long GRBs are now firmly linked to the catastrophic collapse of extremely massive, rapidly spinning stars, hypernovae. When these giant stars run out of fuel, their cores collapse, forming a black hole. But instead of a simple explosion, the collapsing star launches powerful, narrow jets of material outward at nearly the speed of light. It's like a cosmic particle accelerator, focusing an incredible amount of energy into two tight beams. If one of these jets happens to be pointed directly towards Earth, we observe it as a gamma-ray burst. The energy within these jets is truly phenomenal. It's not just the raw power of the explosion, but the way this energy is focused and directed that makes GRBs so incredibly luminous. The material in these jets collides with surrounding gas and dust, creating shockwaves that generate the intense burst of gamma rays. This process is so efficient at converting the kinetic energy of the jets into radiation that for a brief moment, a single GRB can outshine everything else in the universe. The afterglow of these bursts, visible in X-ray, optical, and radio wavelengths, allows astronomers to study the environment around the explosion and the distant galaxies where they occur. Short GRBs, on the other hand, are thought to have a different origin, the merger of two incredibly dense objects, like two neutron stars, or a neutron star and a black hole. When these cosmic titans spiral inward and finally collide, they unleash a burst of gravitational waves and a short, intense flash of gamma rays. These events are also incredibly powerful, though typically less energetic than long GRBs, and they are responsible for forging some of the heaviest elements in the universe, like gold and platinum. The detection of both gravitational waves and gamma-ray bursts from the same event in 2017 marked a new era in multi-messenger astronomy, confirming the link between neutron star mergers and short GRBs. The implications of gamma-ray bursts are profound. While they are rare in our immediate cosmic neighborhood, a GRB occurring too close to Earth could have devastating consequences, potentially stripping away our atmosphere and causing mass extinctions. Thankfully, such an event is highly unlikely in our galaxy. Instead, GRBs serve as powerful beacons, allowing astronomers to probe the distant universe and study the formation of stars and galaxies in the early cosmos. Because GRBs are so bright, we can detect them from billions of light years away, making them invaluable tools for studying the early universe. By analyzing the light from GRB afterglows, scientists can learn about the conditions of the universe just a few 100 million years after the Big Bang, including the formation of the first stars and galaxies. GRBs have also helped refine our understanding of cosmic distances and the expansion of the universe. Their extreme luminosity makes them potential standard candles for measuring vast cosmic scales, complementing the role of supernovae in cosmology. Each new burst detected adds another piece to the puzzle of our universe's history. In summary, gamma-ray bursts are not only the most powerful explosions known, but also cosmic messengers, revealing the life and death of stars, the birth of black holes, and the evolution of galaxies. Their study continues to push the boundaries of astrophysics, inspiring new missions and discoveries as we strive to understand the most extreme phenomena in the cosmos. From the fundamental forces that govern the smallest particles, to the cataclysmic explosions of stars and the mind-boggling power of black holes, quasars, and gamma-ray bursts, we've seen many contenders for the title of most powerful thing in the universe. But our journey is far from over. There are still more cosmic mysteries to unravel, more hidden powers to discover. Join us next as we delve into the ultimate beginning, the Big Bang itself. We've explored some of the most powerful phenomena in the universe, from the tiny, invisible forces that bind atoms to the cataclysmic explosions of dying stars and the insatiable hunger of black holes. But what about the ultimate beginning? What about the event that set everything in motion, that created space and time, and all the matter and energy we see around us? Imagine rewinding the cosmic clock, tracing everything back to a single, unimaginable moment. We're talking, of course, about the Big Bang, but the Big Bang wasn't an explosion in space, it was the sudden, rapid expansion of space itself. Picture a balloon with tiny dots on its surface. When you blow up the balloon, the dots move away from each other, not because they're moving, but because the surface itself is stretching. In the same way, space itself began to stretch, carrying everything with it. The Big Bang isn't an explosion in space, but rather an expansion space itself. Imagine a tiny, unimaginably hot and dense point, smaller than an atom, yet containing all the energy and matter that would ever become our universe. This was the state of the universe about 13.8 billion years ago. From this incredibly compact state, the universe began to expand, and it has been expanding ever since. But how do we know this happened? The evidence is all around us. First, galaxies are moving away from us. The farther they are, the faster they recede, like raisins in rising bread dough. This is called redshift, and it tells us the universe is still expanding. Second, we see the faint afterglow of the Big Bang itself, the cosmic microwave background, a sea of ancient light that fills the universe. And third, the abundance of light elements like hydrogen and helium matches what we'd expect from a hot, dense beginning. This initial moment, this moment of creation, represents an immense release of energy, though not in the way we typically think of an explosion. In the very first fractions of a second, the universe underwent a mind-boggling period of super-rapid expansion called cosmic inflation. Imagine blowing up a balloon, but instead of taking minutes, it inflates to an enormous size in less than a blink of an eye. During inflation, the universe expanded faster than the speed of light, not by objects moving through space, but by space itself, stretching at an incredible rate. This smoothed out the universe, making it remarkably uniform on large scales. This incredibly brief but powerful event smoothed out the universe, making it remarkably uniform on large scales, and also stretched tiny quantum fluctuations, the inherent fuzziness of reality at the smallest scales, into the seeds of the large-scale structures we see today like galaxies and clusters of galaxies. One of the most compelling pieces of evidence for this early era is the cosmic microwave background, or CMB. Think of it as the universe's baby picture, a faint glow left over from when the universe was just 380,000 years old. This ancient light, now cooled to just a few degrees above absolute zero, carries subtle patterns that reveal the universe's earliest secrets. The energy contained within the early universe was truly immense. In those first moments, the universe was a scorching hot, dense soup of fundamental particles and radiation. As it expanded and cooled, these particles began to combine, first forming protons and neutrons, then light atomic nuclei like hydrogen and helium. Over millions of years, the universe continued to cool and expand. Atoms formed, then stars and galaxies began to take shape. Scientists used powerful telescopes and computer simulations to peer back in time, reconstructing the universe's history from its earliest moments to the vast cosmic web we see today. All the matter and energy that exists in the universe today, from the smallest atom to the largest galaxy, originated from this incredibly energetic beginning. The Big Bang wasn't just a powerful event, it was the ultimate act of creation, unleashing all the potential for complexity and diversity that we observe in the cosmos. And the expansion hasn't stopped. The universe is still expanding today, a direct legacy of the Big Bang. This ongoing expansion is a testament to the initial energy and momentum imparted at the very beginning. The story of the Big Bang is written in the light we see from the farthest galaxies, in the faint glow of the cosmic microwave background, and in the very elements that make up our world. It's a story still being unraveled, as new discoveries and observations continue to refine our understanding of the universe's birth. While the Big Bang itself isn't a force in the traditional sense, the initial conditions and the subsequent expansion it initiated represent an unparalleled display of cosmic power, setting the stage for everything that followed. We've seen how the Big Bang set the universe in motion, causing it to expand. For much of the 20th century, scientists believed that this expansion would eventually slow down, tugged back by the gravitational pull of all the matter in the cosmos. The prevailing theories suggested two possible destinies. Either the universe would halt its expansion and collapse back in a dramatic big crunch, or it would expand forever, but at an ever-decreasing rate, gradually coasting to a cold, dark stillness. But then, in the late 1990s, astronomers made a discovery so unexpected that it shook the very foundations of cosmology. By observing distant supernovae, specifically Type 1a supernovae, which serve as reliable standard candles for measuring cosmic distances, two independent teams of scientists found something astonishing. The light from these exploding stars was dimmer than expected, indicating they were farther away than predicted by existing models. This meant that the expansion of the universe wasn't slowing down at all. In fact, it was speeding up. The cosmos was not just coasting, it was accelerating outward, driven by a mysterious force that seemed to counteract gravity itself. This accelerating expansion implied the existence of a previously unknown energy permeating all of space, a force so dominant that it now makes up about 70% of the total energy content of the universe. Scientists named this enigmatic phenomenon dark energy. Unlike gravity, which pulls matter together, dark energy acts as a kind of cosmic anti-gravity, pushing galaxies apart at ever-increasing speeds. Its discovery was so profound that it earned the 2011 Nobel Prize in Physics for the teams involved. But what exactly is dark energy? Unlike the other forces we've discussed, dark energy doesn't seem to arise from particles or fields that we can directly detect. Instead, current theories suggest that dark energy is a property of space itself, an intrinsic energy woven into the very fabric of the cosmos. As the universe expands, more space is created, and with it more dark energy, causing the expansion to accelerate even further. The evidence for dark energy comes from multiple lines of observation. Besides supernovae, scientists have studied the cosmic microwave background, the faint afterglow of the Big Bang, and the large-scale structure of galaxy clusters. All these measurements point to the same conclusion. Something unseen is driving the universe apart. Yet despite its overwhelming influence, dark energy remains one of the greatest mysteries in modern science. We do not know its true nature, its origin, or whether it will remain constant or change over time. The implications of dark energy are profound. If it continues to dominate, the universe will keep expanding faster and faster, leading to a future where distant galaxies slip beyond our view, and the night sky grows ever darker. Some theories even suggest a big rip, where the expansion becomes so extreme that it eventually tears apart galaxies, stars, planets, and even atoms themselves. Alternatively, if dark energy changes over time, the fate of the universe could be very different. For now, dark energy stands as a powerful reminder of how much we have yet to learn about the cosmos. As we look out into the vastness of space, we are confronted by the reality that most of the universe is made up of something we cannot see, touch, or fully comprehend. Dark energy is the ultimate cosmic enigma, a force that shapes the destiny of everything, from the smallest atom to the largest galaxy cluster. The quest to understand dark energy is one of the greatest scientific adventures of our time, and its secrets may one day reveal the true nature of reality itself. In the end, there isn't just one winner. Power in the universe takes many forms. For a few seconds, gamma-ray bursts can shine brighter than every star combined. Over millions of years, quasars burn with incredible endurance. On the smallest scales, the strong nuclear force holds atoms together. On the largest scales, dark energy pushes galaxies apart. And holding it all together, gravity shapes the stars, the galaxies, and the cosmic web itself. Each of these is powerful in its own way. Together, they remind us that the universe isn't ruled by a single force or event, but by a balance of many powers working side by side. Our journey through the universe doesn't end here. At Physics and Cosmos Academy, we'll keep exploring the greatest mysteries of physics, astronomy, astrophysics, and cosmology. We'll look at how stars are born and how they die, the secrets of neutron stars and black holes, the fate of the universe itself, and the latest discoveries that are changing the way we understand reality. If you enjoyed this journey, please like the video, share your thoughts in the comments, and subscribe to join us. The universe has many more stories to tell, and together, we'll keep discovering them.